Guys, welcome wherever you are. I'll just say welcome and to our continuing series of webinars that we've been doing here. We'll get right into it. So let's talk about a little bit about, what is electrical power measurement monitoring. And again, if you, if you think about it, it really depends. It can mean different things to different people with different applications. There is as Ross briefly touched on, there is a distinct difference between the two, where measuring usually means real time. For example, I have a DVM, digital voltmeter. I'm going to electrical panel. I want to see what the present reading is. Is it 120 volts? Is it 480? Is it 277? So it usually means real-time, instantaneous reading. And these are the products that you typically would use. As I said, your typical DVM, digital voltmeter, or if you have fixed metering, like panel meters and things of that nature, they're performing the measurement, which means that they don't have the ability to store data, if you will. And that's a big part of what monitoring does. And monitoring simply means the recording of parameters over time. So a typical example is that I want to see what the building energy usage is over a 30-day period, which is the typical billing cycle. And so I would have the instrumentation that is suited to do that. So again, the takeaway from this slide here, you have measurement, and which is basically real-time instantaneous reading, which is versus monitoring, which typically means recording of any power parameter over a period of time. And so again, as we peel back some layers here, where would I use measuring versus monitoring? Again, it relates to instantaneous measurements. Usually, I see it, most applications that I see are usually in the spot checking. Typically, it's a voltage or current, but it can include any of what I call the basic meter parameters. In addition to voltage and current, your watt, active power, which is kW, apparent power, reactive power, power factor, and so forth. And so usually any time one wants to spot check, hey, I suspect I may have a low voltage reading at this particular outlet, you're usually going to deploy something like a digital voltmeter to spot check. Monitoring could relate to that same application or same scenario where I'm suspecting I'm getting low voltage at a let's say an outlet. So I want to monitor over the period of time to see what that profile is. And again, that sort of is the opening to what I call power monitoring, whether it be power quality monitoring and whether it be just load monitoring. That kind of opens the door to those type of applications, because when one monitors over a period of time, you're looking for changes. Do these changes coincide with things that are happening within the facility? That I have a low voltage at, let's say at 9 o'clock in the morning, where there was maybe some construction going on. So you can see how this kind of leads into your typical power monitoring survey, PQ survey, where you're monitoring over a period of time. And then your application might include one or more above. And typically with today's instrumentation that you see on the market now, obviously they have the ability to provide what we call real-time measurements or instantaneous measurements, but also have the ability to record those measurements to memory. And again, there's general types of power monitoring. Typically if you're involved in energy management, it's how much power, the power flow, especially in today's world, people are really concerned with the direction of power flow. When you have alternate sources of energy, it's very important to know when the power is flowing, what direction it's flowing, and things of that nature. And then of course, power quality. Power quality is what made the Dranetz name legendary as far as power quality. How good is the power? Another way you can think about it is reliability. How reliable is the power? And things of that nature. And there are instruments that are suited to, depending on the application. It might be something a little bit more on the upper end, where you want the ability to record not only power quality, but also you hear the term power analyzer. So when I record the data, I have the ability to analyze the data, waveform data, things of that nature. So your application may call for something a little bit more on the high end. Your application might call for something where it's kind of in the middle, where I basically want to detect if I have a power quality event. I still want to monitor for, remember I'm using the word monitoring, so I want to monitor these parameters, the power parameters over time. Or I may have something in which my mindset is completely different. I want to be permanently installed, but also have the ability to record and provide instantaneous data as well as power quality data. Now, as Ross mentioned earlier, there are some similarities, but they are different. And it usually relates to what I call resolutions. And so if you have a product that is engineered from the ground up for, let's say, energy management applications or energy recording applications, the resolution is typically in seconds. Accuracy is usually high. You'll have 0.02 class, accuracy class, 0.02s accuracy class, things of that nature. These are typically used in revenue or billing applications. And then, of course, you have power quality, and the resolution for power quality is in microseconds. Why is that? Well, you can have power anomalies or power quality events whose duration may be in the microsecond range. And so obviously you want to have the instrumentation to be able to record that. High accuracy is important, but it's really not required because, again, the main focus is, power quality monitoring, PQ detection, things of that nature. But again, today's instrumentation being really sophisticated, have the resolution for power quality applications, but also have high accuracy if your application should change where you might be revenue monitoring or billing, things like that that's involved. The takeaway from this slide here, and I've seen it too many times in my career, is that often the user will typically what I would call misapplied technology. They would purchase or acquire instrumentation whose resolution are in seconds, and then will be severely disappointed when they try to use it in PQ applications, when they're trying to detect these microsecond power quality events. And so the best scenario here that, today's instruments having the ability to do power quality and energy would typically have resolutions in the microseconds. So you can use power quality if it's designed from the ground up for power quality applications where your resolutions is in microseconds. You can use them in both applications. I can use them for PQ applications. I can also use it in energy management applications, but I can't vice versa. So that's the important thing to remember. Sometimes what I've learned in this business is that you do get what you pay for. So although the energy meters might be a little less costly, you wind up paying more in the end if you have what I call misapplied technology. So I have a meter that's designed for energy management applications, but I'm trying to use it in a power quality application. And again, I'll be disappointed with the results. So again, we talk about power quality or PQ versus energy applications. Typically, what type of applications do I see in energy? Well, it's the obvious, where and when the energy is consumed, determine energy costs. Anytime you're involved in any type of energy management application, what's the end result? The end result is always about determining energy costs and how to manage those costs. And it might be individual loads, or it might be the entire facility. We see a lot of scenarios where you compare it to the utility bill. Is the utility bill correct? And so we see our instrumentation, or we see instrumentations like designed for energy management that are used in those applications where the utility bill is inaccurate because the meter is inaccurate and so forth. So we see that. And then of course, ongoing energy management, verified savings. There's a lot of what's going on in the industry where, consumers or customers will deploy energy saving devices. You'll hear the pitch, this device can save you 30% on your energy bill. Well, how do I know that if you're not monitoring? And so right here, you're getting into what we call continuous monitoring, a 24/7 monitoring. And then of course, the power quality. And another way I like to look at power quality is I like to look at it as reliability, power reliability, voltage reliability. So those are the things that I look for. Determining, what's the number one out of these bullets here. It's usually this here, determining the cost and source of energy problems. And you're getting to energy, what we call power quality troubleshooting and so forth. And these two kind of relate, the second bullet and the last bullet. Once I determine the cause and the source of these problems, then I have the information that I need to select the proper mitigation. And again, once you deploy the mitigation, you have to monitor it to make sure the mitigation is continually mitigating the problem. These devices don't last forever. And so there's a need to always continuously monitoring to make sure the mitigation is doing what it's supposed to. Now, when we talk about types of power monitors, and I always like to use the word power, because power can be power quality, can be energy management, can be both. So I always like to use power as far as a global description of power monitoring. But you have two different applications. There's portable. And portable usually comes into play where something has to occur, something has to trigger to deploy monitoring. And so that puts it in the category of what we call reactive. So something's happened, you deploy the instrumentation, you collect the information, you review the information, and then you deploy the mitigation. That's usually the path that it follows. And again, you have other things that'll help you along the way as far as desktop applications for software, applications for data reporting and things of that nature. You have different classes of portable monitoring, to data loggers, to where you're just simply looking for trend data, you're looking for detection of any power quality anomalies. And then you also have what we have power analyzers. The difference between the two is that power analyzer is going to perform all the functions in terms of power monitoring that a data logger will do. But in addition, it provides data analysis. So once I record these power quality anomalies, I now need to analyze that. What's the drawing a blank here. The purpose in analyzing it is basically determine what mitigation do I need to apply to correct the problem. So when you look at the difference between the two, you have a detector, data logger versus a little bit more advanced that performs all the functions that a data logger PQ detector do, but also has the ability to allow you to analyze data as well. Now, when we talk about permanent, then where it's a different application altogether, it's usually proactive. The mindset is usually you kind of evaluate what your processes is, how you would be impacted by PQ events, what would be the significance if you're impacted by a PQ event, what would the cost be if you're impacted in a negative way, and then you take steps as far as what do we need to do to help us avoid that. And so the first step is obviously you want to monitor the power. If you're concerned that you could have a PQ event that can negatively impact you, then obviously you want to monitor for that. And of course, you want to monitor in what we call a 24/7 scenario. So you're monitoring 24 hours a day, 7 days a week. It's usually permanent. It's usually installed for the life of the system. There's different types of meters, from energy to PQ to both, other types of metering. There's ways in which you would mount it, from a panel mount to rack mount to wall mount, with or without displays. Since wiring is permanent, I should say permanent, screw terminals are the most common as far as voltage leads and clip-on connectors. Communications is strong communications is essential. We find these permanent types of monitoring in substation environments, industrial, data centers, which I like to call mission critical, and basically other applications where permanent proactive approaches will be deployed. We do see in residential applications with residential revenue meters. And again, the key is to have a system software, if you will, or a centralized platform that automatically polls the meter, stores the data, and allows the viewer to analyze the data. When you're dealing with portable, the retrieval of data is usually a manual process. Either you're going to establish a communication link to the instrument, and you're going to use the appropriate desktop app to download the data. That's a manual process. Or you're simply going to have a storage device like a flash drive or something along those lines, and you're going to insert it into the monitor and then download whatever data recorded by the monitor onto this device. Again, what we call a manual operation. And when you have a permanent application, then it's usually automatic and it's usually performed by a system software platform. So when we kind of peel back a couple more layers, here's your typical architecture of a fixed base system. You have your various types of monitors at various different locations. Usually with a fixed base system, you're always going to have monitoring at the point of common coupling. That's where the customer meets the utility. There's several benefits that you get when you start there. A lot of times, potential customers will come to us and say, yes, we're looking to deploy a permanent system. Where do we start? And so usually you always start at the point of common coupling. If you have multiple feeds going into a facility, then ideally you want to have monitoring at each feed. And then from there, you would go down line until you reach the critical loads. Another way of putting it is you want to monitor the input and the output to the critical load. So a lot of times it might involve mitigation devices in between the point of common coupling or the utility and where the critical load is. There might be a UPS, for example. So in that scenario, you would monitor the input of the UPS, which is your feed coming in from the utility, and then you monitor the output of the UPS, which essentially is the input to the critical loads. So if you go back to that formula, I want to monitor the input to the critical loads. You might have the feed going directly past and may not be any mitigation involved to the critical load, and you're basically talking, one instrument per se. But again, so you have your individual monitors at the various different locations. You have a centralized platform that is polling the instruments and storing the data. And then, of course, there's access to the data. Everyone these days are using the web browser as far as the portal accessing the data. And so that would be your typical setup. How is that data being viewed? Ross touched on earlier, the visualization of the data. You typically would have, might be an example of how you would visualize the data that's being pulled by a centralized platform, whether it be a single line, whether it be a dashboard, or whether it be a combination of both. And obviously you have your visualization would have things like alarming and notification of events, email notifications, things of that nature. So the benefits of power monitoring, why do we do it? And when you really boil down to it, it's really three things. There's problem avoidance. And again, proactive monitoring can really help in that regard. We've seen many cases to where detection of what we call precursor events or pre-fault events. These are events that are anomalies. You're not having issues at that time, but it's sort of an indication that something may be more sinister down the line. And so usually the attitude is that if I'm recording these precursor events and they appear to become more numerous and higher intensity, then that's the indication of trigger the investigation part of it to find out why these precursor events are happening. And then that usually leads to the avoidance of having a major failure. So problem avoidance is definitely one of the benefits. And then of course, understanding your facility. If you don't monitor it, you can't measure it. If you're a facilities manager and someone says, how much energy did we use last month? It would be your benefit to be able to have that information. Or if someone says, well, my VFDs just tripped offline. Can you tell me if it was power related? And so having the knowledge and understanding your facility is a big benefit as far as power monitoring. And then of course, answers. When that very same question, someone will ask, did my VFDs trip offline because it was power related? And because you have that knowledge and understanding of facility, you can quickly react to problems. You can tell them yes, no, and so forth. And we do see the finger pointing, and this relates to troubleshooting. And you could say that about anything. It doesn't necessarily have to be power related, but when you adopt a troubleshooting procedure, you start eliminating components that can cause the problem until you finally have pinpointed or zero in to the component that's causing the problem. We see in our business all the time where we have the finger pointing. We're sitting here in a classroom, the lights flicker. One might think, well, it must be the utility that's doing something. That's the initial reaction that you have. But a lot of times you do the investigation and you find out that it's really not the utility at all. It may be something going on within your facility. So what do we measure? And, typically, and again, I mentioned we do see some instances of residential monitoring, but in most part, it's usually industrial or commercial. And here you have the typical circuit types from single phase to split phase. Split phase is typically what you see in residential facilities. And then of course, when we get into industrial and commercial, I'm getting tongue tied for whatever reason. Maybe I need another cup of coffee, or maybe too much coffee. But when we get into industrial or commercial applications, then typically you see what I call your multi-phase circuits, three-phase delta, three-phase Y. But let's look at some of the connections, because Ross touched on a very interesting point early on about, making sure that we have the proper connections in order to get the most accurate data. We see a lot of instances where improper connections can result to data not being as accurate as it should. So let's look at these. First of all, I want to talk a little bit about Blondel's theorem, how it relates to three-phase delta two-wire. So Blondel's theorem really relates to what's called the 2-watt meter method. The 2-watt meter method is a way that you can determine totals for a three-phase, three-wire circuit just using 2-watt meters. The watt meters being your CTs. Your CTs combined with your voltage connection makes a watt meter. And so one would think, well, for a three-phase, three-wire circuit, don't I need 3 watt meters in order to determine the totals for the circuit? Blondel's theorem says that you only need 2. And there's a lot of installations out there in which you do have just the 2 watt meters. So I just want to preference before we go any further by mentioning Blondel's theorem. Typical single-phase circuit, pretty straightforward. But we do see in a lot of instances here where the connection might be just what we call line to neutral. And in my opinion, if you just adopt the line to neutral connection along with current, then you're missing half the picture. The rule of thumb should always be if there is neutral to ground present, then you should monitor neutral to ground. You even have an option of monitoring neutral current. If you're getting to scenarios where you think you might be having tripling harmonics or what we call zero sequencing harmonics, in which you need to monitor the neutral, then there's an option there if you have the correct instrumentation in which you can monitor the neutral current. But you should always monitor neutral to ground in this setup here. I've seen too many applications, spoke to too many people that do not. Obviously, you want to monitor current. This scenario here, this diagram here is going to give me both power quality monitoring and energy monitoring. Obviously, because I have current and voltage, I have the energy component of it. Current is also very important as far as determining directivity or the source of the event. And so having the current information at the time you have the voltage event is a key component to determining, if we go back to a few slides earlier, the finger pointing. Do I point to the utility or do I point to the load? So that's very important there. Then we have split phase. This is pretty straightforward as far as the connections are concerned. You can see here we have our current connections on each one. And then we basically have what is called a to neutral or B to neutral measurement in split phase. Today's instrumentation are sophisticated where they actually give you a phasor diagram of your connection. And that's a very important tool in helping you determine if you have the right connection. This is probably one of the most common 3-phase 4-wire Y. The 4-wire indicates the number of current carrying conductors. And we could probably guess what that is. You have your 3 phases and then you have your neutral. And of course, it's 3-phase. The measurement here is your typical A to neutral, B to neutral, C to neutral. And then of course, we're always, if there's a neutral involved and the ground involved, we're always monitoring the neutral to ground. And again, we do have an option. This particular instrument here has an option which will allow us to deploy a 4th current probe, or, excuse me, current probe or CT to monitor any neutral current. And then of course, you have your phasor diagram that helps you aid you into making sure that you have a current connection. Here we this 3-phase delta, and again, this kind of touch on a little bit on Blondel's theorem here. This is the typical 3-phase delta in which we essentially have a 3 watt meter method. Okay, and you can see that your voltage connections are your classic A to B, B to C, C to A using the appropriate channels. We have our current probes on each leg. That gives us our classic 3-phase, 3-wire, 3-probe delta measurement. Okay. But then when we talk a little bit on Blondel's theorem, here where this is your classic 2 watt meter method. So your connections, your voltage and current connections are such where I basically have created 2 watt meters to measure the power totals for this 3-phase circuit. Okay, and again, there's a lot of older installations that are out there that are still using the 2 watt meter method as far as determining power totals for a 3-phase circuit. Where it gets confusing is, and it's really, is that the phase voltage and line current, because you can't actually monitor a phase current, so you have access to line current. So the relationship, there's an inherent 30-degree difference between the two. Again, at the end of the day, the total power works out fine because we're basically using Blondel's theorem. But I could remember in the early days where instrumentation didn't have a three probe method or 3 wattmeter method for a delta circuit, but yet will give you real-time readings on all the phases. And when users will often go and view single phase or single channel information for VA, VARs, and power factor, they look at these numbers and then they take the numbers and they try to put it into textbook equations and wondering why that the totals don't work out. So it does cause a lot of confusion, but once you peel back some of the layers and know a little bit about Blondel's theorem, it kind of all makes sense in the end. Let's talk about some transducer considerations. Ross touched a little bit on it earlier. Again, the definition of a transducer and really the way that it applies to power monitoring, it comes down to your PTs, potential transformers, and CTs, current transformers. So it really boils, in the power monitoring world, it comes down to basically PTs and CTs. And so when we talk about a voltage transducer, most of the power monitoring that takes place, particularly from a troubleshooting standpoint, usually takes place at the low voltage level. The low voltage level meaning up to 600 volts. And so in those scenarios, if the most instrumentation that you're using, if it's UL, it's probably maxed out at 11, although I should say 600 volts. There are some instrumentation that will go up to 1,000 volts direct connect, but most are 600 volts. And so there's no PT, no voltage divider, no transducers that are needed for direct connect. And that's probably the recommended scenario. I've seen scenarios where it might be a 480 application, but there's PTs that in which the user would connect to, and that should be avoided because the PT itself would act as to attenuate certain events based on their frequency. So whenever you have the opportunity to make a direct connection, as long as you're staying within the safety parameters of the instrument, that is the recommended method, especially if the application is PQ, power quality. Potential transformers that we see are typically used to step down the voltage to a measurable level by the instrument, which are used in medium and high voltage applications. A very common application is 4160, 4,160 volts. Obviously, any instrument, I don't know of any instrument today that's going to be able to take 4160 direct. And so typically you're going to use, you usually piggyback off existing PTs. For example, if you're walking through your switchgear and you see these panel meters, particularly the analog panel meters. And the analog panel meters, it's a very good chance that the analog panel meter says that it's 4160. You can almost guarantee that 4160 is not going directly to that panel meter. It's actually coming off, piggyback off a PT. Whether it be a medium voltage or whether it be high voltage applications. Okay. Some other things to consider here is that if you're in a scenario where your power quality troubleshooting and maybe it's a medium voltage application and you don't want to piggyback, you don't want to deploy PTs, potential transformers, because of the frequency consideration, then one alternative is a voltage divider. And a voltage divider has a better bandwidth. Ross talked on that earlier about bandwidth. has a better bandwidth, because the idea is not to attenuate any PQ events that are causing the problems. You want those PQ events to reach the instrumentation and not be attenuated by any in-between devices. So we find that a voltage divider has a better frequency response to allow those transients and allow those events to go through. As far as RMS events, if it's RMS events that you're detecting, they're usually not frequency sensitive, but when you get into what we call transient events, and transient events are these variations in voltage or current whose duration is less than 1 AC cycle. So now there's a frequency component there. And if you want to be able to record those with any power monitor that you might be using, you want to make sure, again, that the in-between device is not actually attenuating them. So that's very important when you're deploying these devices. Current transducers, usually, again, no direct connection. The consideration that you want to keep in mind with current transducers as far as how do you connect to the circuit, how do you pick up the current? There are current probes. A current probe, again, is a form of a current transducer, because the output of a current probe is not current. The output of a current probe is a voltage that is fed into the instrument that interprets the current. So we use the term CT, we use it interchangeably all the time to describe a current probe, which technically it's not a CT, it's a current transducer. A CT, a true CT, as you well know, will basically have a current primary and a current secondary. And in the industry, it's usually 5 amp secondary or 1 amp secondary, 5 amps being the most common. If you have a current probe, again, that we sometimes categorize as a CT, we'll usually have a 1.5 volt output, a 3 volt output, and the very common 333 millivolt output. The key there, if you're using any of these current probes with any instrumentation, obviously you want to make sure the instrumentation can handle these voltage outputs from the probe. We typically see these in portable applications, because in portable applications, you typically will have a set of current probes or CTs that come with the instrument. And so that's one thing to keep in mind, is that those are technically transducers, which will have outputs that might be in these ranges here, or it might be something unique otherwise. CTs are generally, we see in fixed applications. We usually either deploy CTs, usually split cores, because usually there's not a shutdown that's required. A split core CT, you can actually put on without having to call for an outage. Solid core CTs, you have to do just the opposite. But these are typically CTs, so they have a current primary and a current secondary. A very common ratio that you might hear is 2,000 to 5, or 3,000 to 5, or 600 to 5. So those are some of the common things that you might hear. You have different types of CTs, clamp-ons. Again, we're kind of using the term CT, but in this case, it's actually a current probe. But again, you have the different voltage outputs. Again, 333 is the most common. The very popular flexible CTs. These are extremely versatile. I was going to say flexible, and no pun intended, but I'll just say versatile. They're versatile in the sense that they can easily get around conductors. They're versatile in the sense that they have multiple ranges. So it's like having 3 sets of CTs in one package. Depending on the dimensions of the bus that you need to get around, they come in different lengths. 24 is the most common, but there's lengths of 36, 48. And again, these are transducers. So they're going to make a current measurement on their primary and then provide a voltage output of either 1.5 volts or 3 volts. Okay. The other thing I should mention about CTs is their bandwidth. They usually have a high bandwidth. And if the instrumentation has the ability to monitor a current transient, back in the old days, they were called impulses. Today, in today's world, they're called transients. But if the instrumentation had the ability to monitor a current transient, then obviously you want to match it up with CTs or current probes that has the bandwidth to pass through transient. Just like you're monitoring voltage, monitoring current, I should say, you're monitoring current during a voltage event, and then depending on what the relationship of current during the voltage event, you can determine the origin of the voltage event. Same applies for transients, except that we're dealing in a much shorter time frame. So if you have the ability, again, the instrumentation has the ability that during the voltage transient, where did it originate from? Was it upstream of the monitoring location? Was it downstream? And if you have the proper current probe that has the bandwidth, and you have the instrumentation that is capable of recording current transients, then you can use that same relationship to determine the origin of the transient itself. Different types of CTs and again, now we're getting into the true definition of a CT, a current transformer. It's going to have current primary, it's going to have a current secondary. And it's usually going to fall in the 5 amp or the 1 amp. And you're talking the difference between the two is solid core, which is usually more accurate, usually cheaper. But the inconvenience is that you usually have to call for an outage because you have to break the circuit to put the probes on. Now, in the construction phase, if you're building the new gear, then it's an advantage to have a solid core. But most of the time, when you're installing power monitoring instrumentation, fixed monitoring in particular, after the fact, it's usually a retrofit application. And so a split core is more convenient in those applications. They're a little bit more expensive. The accuracies between a solid core and a split core, although the split core is a little bit more accurate, it's not that big of a difference as you may think. Today's generation of split core CTs are fairly accurate, so you can use them in revenue applications. Of course, as always, the most important thing is the size of the bus or conductors that you need to get the probes around. You'll hear terms thrown around like 5 sets of 500 MCM, things of that nature. You want to make sure that your CTs are big enough to go around all the sets per phase, not just one. There was back in the old days, there was a very common practice in which if you had multiple sets of conductors per phase, the practice was, okay, I'll put a CT around one conductor, one set of that phase, and then just do the math to extrapolate what the current might be. Again, because you have imbalances, you're assuming that the current flow and all your conductors are the same. If they were, theoretically, you could get away with that, but in the real world, they're not. So the best way to get the most accurate is to make sure you have your probes go around all the conductors per phase. Okay. The other thing that comes into play is polarity. All current probes, all CTs, they have some form of polarity markers. And the polarity markers would normally indicate the direction of current flow. So current flows from the source to the load. You want to make sure you observe the polarity when putting on the CTs. The other thing to keep in mind is that you won't see reverse polarity of your current just by reviewing the amperage readings. It's not going to show you a sign if you have a reverse polarity on your CTs or your current probes. Where you're going to find that is basically in your power readings. So when you have your power readings, and power reading says that you're negative on one leg, then it usually means one of two things. Either you have power flowing in the opposite direction, which might be the case if you're dealing with an alternative power source, or the most common, your current probe is reversed. Of course, there's the safety considerations. This brings out a very common thing that I see as far as, when a CT is rated at 600 volts environment, you want to use it in a 600 volt environment. I've seen scenarios where the end user will say, well, it's 4160, but the conductors are insulated. And from a measurement standpoint, you can probably get away with that, but that doesn't necessarily mean that you've taken the best safety practice in that regard. So you want to, I tend to be conservative in those areas. You want to stick to the manufacturer's instructions and don't try taking shortcuts. Measurement concerns, PTs and CTs can act as low pass filters. I touched a little bit on that. So you always want to keep that consideration in mind. PTs and CTs may not be as accurate as the measurement of the instrument. That's true. So, when you think about accuracy, you want to think of it in overall accuracy. So you have the accuracy of the CT or PT plus the accuracy of the instrumentation that's making the measurement. So you have the overall accuracy. In general, CTs will typically have an accuracy of around 1%. You can get into some revenue applications where the accuracy is a little bit tighter. But in generally speaking, an overall average, your accuracies are going to be somewhere in the 1% range. Okay. And again, it's very important that you have the proper selection of CTs or PTs if you're deploying PTs in your application. If you don't, they can negatively affect your measurements. So you'll want to keep those things in mind.